Hello, this is LNT Manish. I'll share my screen. Today I'm going to speak about relevance aggregation. Hmm. The first paragraph is summary. The study article primarily focused on the challenges people face when implementing neural networks for a range of applications and provides a method to make the process easier for users to understand. According to the authors, the main challenge users may experience when using such predictive models is that results may be challenging to grasp because they are sometimes referred to as black box models due to their sophisticated nature. Mission bias and mistrust of predictions have also been raised as issues in the study, mostly as a result of the potential for problematic forecasts in the form of racial or gender bias. As a result, the authors have provided a solution using relevance aggregation, which charts the relevance determined from multiple samples as learned by the neural network and provides a score for each input characteristic. Additionally, they provide two methods for visualizing the master patterns, which enhances the understanding of models. They have also focused their research on unstructured tabular data and the algorithms that work best with it because it is commonly used in scientific and commercial applications. To present the idea of relevance aggregation, a number of articles on the application using LRP, experimental datasets on varied uses, fluctuation analysis, and visualization methodologies were assessed. One of the techniques suggested for discovering the distinctive scores applied to the input features for the network output for each sample was layer-wise relevance propagation, MRI-based hypertension classification, the categorization of audio signals, and the forecast of macroscopic and microscopic malignancy profiles, facilitating knowledge discovery and choice interpretation are some of the studies that have utilized LRP. When performing regression or classification, relevance aggregation looks for the input features that are most pertinent to its predictions. This is accomplished via an algorithm like LRP. The method uses the absolute values discovered to assign a value that indicates the relevance as a positive or negative integer for each input for each sample. In order to properly meet the requirements of the specific application, the values are even further scaled to guarantee that all examples are given the very same importance when aggregated. This avoids comparison bias in benefit of samples with more ambitious goals. The goal values ranges are initially used to categorize the data into classes. The ultimate score is computed as the mean of the class scores to make sure that every class is material to the outcome. The authors choose to use the geometric average of the quantitative data that were encoded to retain the value of 0 or 1 in order to prevent the development of artifacts when distinct category features had different encoding periods. A table heat map and a weighted TSNE method, both of which were inspired by Black et al., were offered as two methods for improving the data's presentation and interpretation. For the experiment, datasets from the real world and artificial ones were both utilized. The attributes that earned the highest rankings utilizing the applicability aggregation approach did have a significant change in the results of the prediction model. According to Samuel et al. Studies, using artificial and real-world data and the preference analysis they detailed, Backchatter served as inspiration for the weighted TSNE approach, and the table heat map was offered as two methods for better visualizing and explaining the data. For the explanation, for the experiment, datasets from the real world and artificial ones were both utilized. The attributes that earned the highest rankings utilizing the relevance aggregation those did result in a significant change in the output of the prediction model. According to Samuel L. Studies, using synthetic and real-world data and the perturbation analysis they detailed, though neural pathways have been used frequently in many areas, a considerably larger range of applications may be found for them if people were to understand how the technology works. The authors highlight this problem and suggest a relevance aggregation approach, which is evaluated using a range of artificial and real-world datasets. This is done to show that method can be used to distinguish between relevant data and original data, as well as accurately determine the most crucial aspects in network forecasts. The strategy was broadened to take into account neural nets with insufficient training, enabling detection of biased mission behavior or flawed pointless rules. The study was quite easy to read, and the references to the paper that were connected to the experiment give readers a feeling of continuity and aid in the understanding of the author's thought process. The flaws in the research were pointed out explicitly, and solutions were suggested along with the relevant evidence. The author's experiments were contrasted using both synthetic and real-world data, enabling a full examination of the results. Impact visualizations were included with every analysis that was connected on the data, including perturbation analysis of the key aspects of the paper in the approach the authors took to solving the issue using a widespread application of neural networks. They evaluated a suggested approach using data from these disciplines to show how neural networks may be used in the fields of medicine, business, and even education. Data provided offers enough proof to back up the relevance aggregation strategy as well. An experimental design was required because the authors had to change the attributes to be employed for the prediction in the study issue in order to examine the results of previously established groups. Therefore, the chosen study design was suitable for this particular research issue to evaluate whether and how firmly the factors were related to each other and how they impacted the result. A step-by-step design of experiments with step-by-step analysis was the ideal approach. Although the research focused on how tabular data was understood, it did not sufficiently show how the trial's results might differ from data acquired from images. The treatment of categorical data in the study may have benefited from further emphasis. The recommended LRP algorithm caught my attention as I was reading about it, and I'd like to learn more about it and its applications. I'm also interested in learning more about the TSNE visualization method. Thank you.